analytics, we say we are working under the domain of data science. So again, this is the focus that determines what terminology you should use. So if your core focus is on identifying hidden patterns, knowledgeable patterns, we can prefer using the term data mining. If our core focus is on coming up with predictive models, we should prefer using the term machine learning. If we are, our core focus is on giving exploratory analysis to the data, visual representation of the data, we are working with big data also, we are processing these algorithms under Hadoop kind of environment, we can prefer using the term data science, that we are working under the domain of data science. So it is always the focus that determines which terminology to use. But all these terminologies, whether it is data mining, whether it is data science, whether it is machine learning, the core principles are always the same. I hope this clears.
Yes, sir. Thank you very much, sir, for clarifying the doubt. And one more thing, sir, but I learned that when we are having a small size data set, then only we can implement the data mining algorithms. When we are having large amount of data, then we can apply the machine learning algorithms. Yes, I learned like that. Is it true, sir?
Yeah, actually, for demonstration purpose, because currently this is FDB which is happening, and for demonstration purpose, the academician always prefer working with the small data. But the same algorithms can be applied to large data sets also. The only thing is that we don't have access to such large data sets. And number two, if we have the large data sets, we need bigger infrastructure, a powerful infrastructure. And again, on a powerful infrastructure also, these bigger data sets take a lot of time to execute. So for demonstration purposes, we always prefer small data sets. This was the reason why I am also experimenting with small data sets. But if you are in a real life scenario, exactly the same algorithms can be applied to the large data sets also. But behind the scenes, the infrastructure needs to be very powerful.
Thank you very much, sir.
Yes, thank you, ma'am. Okay, so one more, practical demonstration we will take of, a DB scan. So if we consider a very complex, kind of data sets, modes. So this last code snippet, after that we will, start the discussion on PCA, principal component analysis. So let's make a complex, data set now. X, Y is equal to make modes, number of samples being equal to 200, noise let's say is equal to 0.05, random state is equal to 0, so make modes needs to be imported.
Sir, a small query, sir.
Yes, ma'am, please.
Sir, DB scan especially works on data with noise, sir. Can you show one example with noise, how the DB scan class it for clustering?
Ma'am, I didn't get you. Can you come up again, please?
Sir, DB scan especially to handle the noise data, sir.
Yes.
Can you take one example data with the noise?
Yes. Actually, in the previous, this was also the example of noise also. Now you see, if you look at these 12 points, so one way of looking at this, that they are not close to each other. You see, even if with these parameters, minimum sample is equal to 3 and EPS is equal to 1.5, we are able to, group these 5 points under one cluster. But in the reality, one way of looking at this, actually, these 3 points are noise, because, these 2 points are lying close to each other and these 3 are different. So that's why, if you don't mention these tuning parameters and you depend on the default value of these parameters of DBS. So now it is handling noise. So now if you give a visual representation, you see all the points have been plotted with the same color. That means now your algorithm has considered all these points as the noise. So again, the point is that with these parameters, which we specified, like over here, minimum number of samples equal to 3 and EPS that the 10th point is a noise. Similarly, if this second value came out to be -1, we would have said that the second point is a noise. So this is how you can, see the noise also. You can give a visual representation to the noise, and that point can be plotted with a different color also. So this is a special terminology that, DBScan uses. If it returns -1, the point needs to be considered as noise. If the values are in the form of 0, 1, 2, 3, they are exact clusters. So I hope this clarifies your point.
Sir, thank you very much, sir. Can you show the different types of points in the form of a graph?
Different types of points. For that, we need to make a different, we need to experiment with different, values of minimum samples and EPS. So should we do that now?
Yes, sir.
Okay. So let's say then the minimum samples be 1 and EPS be 1. So with that, okay, there is no -1. So with 2 and this is equal to 1, this is also 2. So again, now see there are only 2 clusters, 0 and 1 only. So this is a hit and trial method now. So again, I think it would be better if you do it at your own. You experiment with the different minimum sample and EPS values. So you will encounter certain situation where few values are -1 and few values are not -1. Or let's say if we experiment with minimum sample is equal to 2 and EPS is equal to 1. Yes. So now here you can see this -1 and 0 and 1. 3 values have come up. So 1, 2, 3, 4. The 4 points are noise. Other 2 points belongs to 2 different clusters. So now if I execute this code, so you see the 1, 2, 3, 4, 5. These 5 points are noise, means these purple color points 1, 2, 3, 4, 5. These are the noise, while these yellow and green points are the clusters. Clusters represented with number 0 and 1. So this is now the visual representation of noise also. Noise is given this color, the purple color.
Very clear, sir. Thank you so much, sir.
All right, ma'am. Thank you. Okay, so we were now experimenting with make moons functions. Make moons. Okay, so make moon dataset has been generated. So we need to scale it also. Standard scaler. So scaling is done so that all the data points, all the feature values come under the same scale. Otherwise, what happens that the feature values which are attaining high values, they can dominate the features which are attaining low values. So in order to avoid that dominance, we generally perform the scaling. So you see the output now. This make moon is a very complex, kind of data set. In the it has a complex shape. So you see how the data points are organized. And the default values of DP scans were able to, correctly identify the 2 clusters. You see. So again, if you, compare it with the, diagram that I showed you, like DB scan. So this is a make moon data set, this one. And DB scan has correctly, identified the, 2 clusters. But you can experiment with k-means also. So you look at the k-means. K-mean algorithm probably will not be able to identify the 2 clusters correctly on this k-means or on this make moon data set. And this shows the comparison also between k-means and DB scan, that if you are dealing with S-shape, figure shaped data sets, then DB scan algorithm is better than the k-means algorithm. And you can also experiment with agglomerative clustering. And as per this diagram, agglomerative clustering will also be able to correctly identify the 2 groups in the make moon data set. So this was that demonstration. So this ends our discussion on clustering algorithm. So now we can start discussion on principal component analysis. So I would be connecting to you within 1 minute. Just give me 1 minute. I have to make an important call. So in the meantime, if you have questions, you can come up with. We can discuss this question at last. But after 1 minute, we would be starting with the discussion on principal component analysis. So
Yes,
so
sir.
yes.
Sir, till that time, please show the code, sir. Till that time, we'll be writing, sir.
Okay. Okay.
Excuse me, sir.
Yes, please.
Kindly show this. Yes, sir. Yes. This Moonsafe code we want to see again. Thank you, sir.
Okay. So I'll come back again after 1 minute. Okay, participants, thank you. So should we start the discussion on PCA now?
Yes, sir.
Okay. So let's look at the basics of PCA, principal component analysis. Actually, the higher level field is the data reduction. So we will look at two things: data reduction, dimensionality reduction, and we will see that PCA is one of the technique for dimensionality reduction. So first of all, let's understand what do we mean by the data reduction. See, data reduction techniques can be applied to obtain a reduced representation of the data set that is much smaller in volume yet closely maintains the integrity of the original data. So this is the basic idea behind performing data reduction. To obtain a reduced representation of the data that is much smaller in volume yet closely maintains the integrity of the data. Now here you may ask the question that why we are looking towards the smaller representation of the data. The answer is that if you are working with the smaller representation of the data, that smaller representation may be more efficient to deal with. For example, if your data set is really very large and you are applying the algorithm on all the features, then your algorithms may not be able to produce the results in real time. But if you reduce the number of dimension, if you make the data set smaller by reducing the number of features, then the results can be produced in real time. So obviously, very naturally, the data reduction is advantageous to us. So processing on the reduced data set is more efficient, yet produce the same result or analytical result as on the original data. And data reduction strategies include dimensionality reduction, numerosity reduction, and data compression. So we would be focusing on dimensionality reduction only. Numerosity reduction and data compression, they are different fields of study. We will not talk about them, but yes, one of the technique under data reduction is dimensionality reduction. And what is dimensionality reduction? It is the process of reducing the number of random variables or attributes under the consideration. And random variables or attributes are nothing but in a machine learning setting, these are features for us. And dimensionality reduction method include wavelet transforms, principal component analysis, which transform or project the original data into smaller. So the point to remember is that dimensionality reduction can also be performed via different techniques. Like wavelet transformation is there, then principal component analysis is there, then non-matrix factorization is there. There are some other mechanisms like TSME types of techniques are also there. One of the technique is PCA, principal component analysis, wherein we transform or project the original data into the smaller space. So the big picture is that what we are doing is data reduction. One of the technique for data reduction is dimensionality reduction. Dimensionality reduction can also be performed in a number of ways. One of the way is PCA. And what we would be doing in PCA, we would be giving a smaller space to the original data set to represent it, so that our processing of that data set becomes efficient on different algorithms. So this is the essence behind principal component analysis. And mathematically, this principal component analysis is also called the Corner-Loew or KL methods. It searches for a k n-dimensional orthogonal vectors that can best be used to represent the data where k is less than or equal to n. So what is the idea behind this? So you see, I need a blank screen for that. Anyways, so I can make use of this space. So let's say you have the original data in this space. Okay. So this is, dimension 1. This is dimension 2. This is dimension 3. This is dimension 4. Similarly, there can be n dimension in the data sets. So this is called original space, original data. And this n can be very, very large. What we are doing in principal component analysis is that we are transforming this original space to something called feature space, where each of the dimension in the feature space is orthogonal to each other. So in a higher dimension space, if you are saying that you are coming up with feature 1, feature 2, feature 3, so on up to feature, let's say, k, then these feature dimensions are orthogonal to each other, and they are arranged in the order of importance. Importance in the sense that feature 1 is most important, feature 2 is second most important, feature 3 is third most important, and so on. And there is a specific relation that this k is actually less than or equal to n. So please understand its practical application now, that if your data set has a large number of features and is to the tune of, let's say, 10,000, it's really very inefficient if we are working with such a large number of features. If the same data sets can be represented with a fewer number of features, let's say k is to the tune of 100 only, very obviously, this k implementation with k is equal to 100 will yield the better performance. And this is the philosophy, this is the idea behind principal component analysis, that if you have a original space with very large number of dimensions, you apply principal component analysis, you apply the you transform the original space into feature space, you identify the different feature dimensions, where the feature dimensions are arranged in the order of importance, and you pick the fewer dimensions, and those fewer dimensions can still represent the original data. And if you are moving ahead with a fewer number of dimensions, the efficiency would be more. So in that sense, we are saying that the original data are projected onto a much smaller space, resulting in dimensionality reduction. And PCA combines the essence of attributes by creating an alternative smaller set of variables. So you see, the values, the dimensions in the feature space are really very less than the total number of dimensions in the original space. This is clear from the fact k is very less than very less than or equal to n. So the initial data can be projected onto the smaller set, and PCA often reveals the relationship that are not previously suspected, and thereby allows such interpretation that would not ordinarily result. So this is the basic idea behind principal component analysis. Again, like the expectation maximization algorithm, the mathematical theory behind principal component analysis is really very much involved, very much complex. We would be able to understand PCA from a logical point of view only. So in that sense, few steps, the basic procedure is described. So the basic procedure is as follows. Number 1, the input data are normalized so that each attribute falls within the same range. And you might have noticed that when we applied, this DB scan to Moon's data set, there also we tried to normalize the data, to standardize the data using scalars. So this should be the first step while applying principal component analysis, that you need to normalize the data. The input data needs to be normalized so that each attribute falls within the same range. And this steps helps ensure that attributes with large domains will not dominate attributes with smaller domain. I already mentioned that if there are certain attributes which are attaining, large values, then they can dominate the, features which are attaining low values. Number two, so after normalization, after standardizing the data set, the second step is PCA computes k orthogonal vectors. So I already mentioned that this k is really less than or equal to total number of features in the original space. So again, this is k, the number of dimension in the feature space, and k needs to be really less than is equal to n. So PCA computes k orthogonal vectors. All these dimensions are orthogonal to each other. That provides a basis for the normalized input data. These are the unit vectors that each point in a direction perpendicular to the others. That's why we are saying these are k orthogonal vectors. And these vectors are referred to as the principal components. And the input data are a linear combination of the principal component. So in terms of this discussion, which we made previously, feature 1 is first principal component. Feature 2 is second principal component. Feature 3 is third principal component, and so on. And third step, so please understand the first two steps. First, we have to normalize the data. Then mathematics behind the PCA will give you k orthogonal vectors. These vectors are perpendicular to each other, and these vectors are referred to as the principal components. First vector would be first principal component, second vector would be second principal component, and so on. Then the third step is the principal components are sorted in the order of decreasing significance. So this point I have already mentioned, that first feature, first dimension is the most important, second dimension is the second most important, third dimension is the third most important, and so on. And the principal components essentially serve as the new axis for the data, providing important information about the variance. So this thing was clear from this, mapping also, that this is the original space and this is the transformed space. And the data from original space is mapped to, data in the feature space. So an example has been given for a two-dimensional data sets, like if x1 and x2 are the dimensions of the data in the original space, then y1 and y2 will become the dimensions of the data in the transformed space. And y1 would be termed as first principal component, and y2 will be considered as the second principal component. This principal component 1, principal component 2, and they are orthogonal to each other. They are be at an angle of 90 degrees to each other. That is, the sorted axes are such that the first axis shows the most variance among the data, and the second axis shows the next highest variance among the data. So again, if we consider the data in this way, for example, let's say the data is organized like this. Now, if you consider this direction, so you'll see you will be able to find out, two curves in this data, like one curve corresponding to this data, second curve corresponding to this data. But if you look at the same data from other dimension, see, this is the projection you will get, and you will get only one hump like this. So clearly from this observation, it is clear that this dimension D1 is more important than dimension 2. Why? Because dimension 1 is providing you information about the, groups of the data, whereas dimension 2 cannot provide you information about the groups of the data. So in that sense, we are saying that the first axis shows the direction of, most variance among the data, and the second axis shows the next highest variance, and so on. And fourth step, because the components are sorted in decreasing order of significance, the data size can be reduced by eliminating the weaker components. So this is most important, observation of principal component analysis, that the components are sorted in decreasing order of significance. Again, I mentioned feature 1 is most important. Feature 2 is second most important. Similarly, if you have identified 100 components, this is 100th most important. And we can make a cut at any level. It is data size can be reduced by eliminating the weaker component at any level, that is those with low variance. And using the strongest components, the upper components are the strongest components. The initial features are the strongest features. And using the strongest principal components, it is possible to reconstruct a good approximation of the original data. And PCA can be applied to ordered as well as unordered attributes and can handle sparse as well as skewed data. So again, the fundamental contribution of principal component is this only. If in a practical application, you are dealing with tens of thousands of attributes, and your algorithms are not working efficiently on such bigger feature space, you can transform the data into a lower feature space wherein the features are to the tunes of hundreds only rather than thousands, and it would be efficient for the algorithms to work with that representation. And this reduced representation can be obtained by a principal component analysis, where there is a complete mathematics behind it that tells you how the orthogonal unit vectors can be obtained, how the data can be mapped from original space to feature space. All these things happen automatically, and in scikit-learn you just need to make a few calls to the principal component analysis method. So this was the mathematics, the basic idea behind principal component analysis. So now over to you participants for any questions, for any queries regarding this discussion. Yes, participants, over to you. You can come up with your queries now.
It's clear, sir.
Other remote centers, local coordinators, if you people have any query from your end, you can please type here in the chat window, or you can ask. No query as such here in the chat window, sir.
Okay, ma'am. Okay, ma'am. So if no more queries, ma'am, then we can end the session, I think.
Sure, sir, sure. So I thank Dr. Sarabjit Singh for taking such a wonderful session.
Sir?
So do you have any queries,
Excuse
sir?
me?
Yes, I think there is one query.
Excuse me, sir.
Yes, please, please.
Sir, how is the importance of feature decided? On what basis, sir?
See, when you apply principal component analysis, the first component is identified in such a way that it belongs to feature of maximum variance. So you see, the importance is decided on the basis of variance. If out of 100, let's say, feature, one feature is such that it is giving a maximum variance with respect to the identification of class, obviously that feature will become more important. And this is the philosophy being used by principal component analysis. So whenever you will apply principal component analysis, blindly we can assume that the first component is most important. And why that has been considered as the most important? Because that is the component of maximum variance. Because your algorithm has already looked at the data and it has checked, it has verified that this maximum variance is closely linked with the target variable also, and this feature can definitely be considered as the most important. And there can be other ideas also, but those ideas are not advocated by principal component analysis. Principal component analysis only advocates this very fact that if a feature shows maximum variance with respect to target, then it needs to be considered as the most important. So similarly, if you are coming up with 20 component, first is the most important, second is the second most important, third is the third most important, and so on. So I hope this answers your query.
Sir, clear, sir. Thank you.
Sir, there is one more query.
Yes,
How
ma'am.
to mention the number of output features in PCA?
when you are instantiating, see, just like we instantiated k-means and agglomerative clustering and db scan, so when you would be experimenting with scikit-learn, you can mention PCA is equal to PCA number of components is equal to something. So very easy. When you are instantiating PCA, you simply need to write PCA is equal to PCA in capitals, then in bracket number of component, n underscore components is equal to some components. It can be 2, it can be 20, it can be 200 also. And accordingly, PCA will give you those many components. So with scikit-learn, it is really very easy. Just with the help of that number of components parameter, you can control the number of components of the PCA.
Another is chi-square value similar to PCA?
No, chi-square value is applied to nominal attributes, primarily nominal attributes. And chi-square values give you the correlation between the nominal values. For example, if we consider two attributes, like one is gender and second is reading preference, and we want to understand whether the gender determines the reading preferences, then chi-square test statistics can be applied on that, considering the fact that gender and reading preferences both are categorical or nominal values. So chi-square test is generally applicable to nominal values, but PCA is different in the sense it gives you important components of the original data sets.
Yes, participants, if any other query is there, then you can please ask.
Actually, due to the paucities of time, we could not, do practical work related to PCA, principal component analysis. But otherwise, it is really very simple. As I mentioned, you just need to instantiate it. PCA is equal to PCA, number of components is equal to whatever you specified. Then again, PCA.fit and PCA.transform. So with these three methods, you would be able to apply PCA. So first instantiation.
Along with the previous script, if you can share, then they can practice.
I'll do that.
Yeah. So thank you very much, Dr. Sarabjit, for joining us today for such a wonderful session, and it was based upon practicals also. So it is really appreciated by our remote center participants.
It's my pleasure, ma'am. Thank you.
Yeah. So I hope the session will benefit the participants in implementing their work related to clustering tasks. Thank you very much, sir.
Thank you, ma'am. Thank you very much. Thank you.
So dear participants and all the local coordinators, you are requested to join back by 2:30 for the next session.